Hello and welcome to a wonderful explanation of some interference pattern questions found in your IB book. This is found on page 394. And I just wanted to give you some hints in the first part of this video, and in the second part I will discuss the answers, okay? All right, so let's dig in. So here we have a graph that shows an interference pattern of some unknown at this point in time number of slits. So it says here, graph shows interference pattern. Yep, very thin parallel slits. Yep, we've got our primary maximums, and then we have our secondary maximums all throughout. Secondary. And it looks like we're about out here, for angles, just looking at the problem, kind of thinking about it, all right? And the first part of this question says, justify that the number of slits is 4. So it tells you how many slits there are, and you need to justify it. So you can't take a guess at this. So you have to explain using either a formula or a description. And so for this, you could look back onto page 369, and that will explain what the relationship between the number of slits and the primary and secondary maximum are. For the second one, now this part B says list a total of 4 ways in which a pattern changes, in which this pattern changes if we change the number of slits, if it increases, and their separation stays the same. Now here, it does say 4 in this. I want you to note that it's a 4-point question. Okay, so you need to say 4 things. So within this whole part B, you need to have 4 answers. Okay. So again, it says the total number of slits. So I want you to look from page 369 to 370, and it talks about what happens if the number of slits increase or decrease about their separation. And for part II, it would be best if you used just straight up a formula out of your data packet. Formula data packet. Okay. Oh, and I was going to give you a hint that you'll have 3 things to say about this one and only 1 to say about that. And this last part, part C, is not about like single double slit patterns. It's more about resolution. Okay, can you, what does the slit separation have to be in order to resolve the line? So here you're going to have to calculate something or whatnot. So this would be found on or about page 379. I won't say on or about, it is about. But when reading this question, notice that we've got a couple of wavelengths in nanometers from 2 different hydrogen isotopes. And so here's an application problem of what we would use this for. And we do need to know something about this 15-degree angle. So looking at 15 degrees, there it is. Notice that we're out at 1, 2 of our primary maximas. So that's some information to think about while you're trying to figure out how to how to calculate the number of slits that were needed. Okay? Now, pause the video, do some work, come back, and I'll try to talk you through the answers. Since there are 2 secondary maxima, and we have this relationship where n number of slits minus 2 gives us the number of secondary maxima. So therefore, do like 3 dots or something like that. 4 minus 2 equals 2. There, hey, all that. Just for. Here's how I would answer question A. Count the secondary maxima. There are 2 secondary maximas. So since there are 2, the number of slits minus the number of maxima, is this relationship between slits and maxima, and 4, therefore 4 minus 2 equals 2. There we go. So for BI, let's think. Number of slits increases, but their separation remains the same. So if we have more slits, we have more openings. Well, the primary maximums are going to get brighter. So the primary maximums are going to get brighter. So the primary maximums are going to get brighter, but the secondary maximums, what happens to them? Well, secondary maximums, they get harder to see, or less pronounced, I think as the book says, harder to see or less pronounced. And then the primary maxima, actually, even though they're brighter, they get narrower. Okay, so primary maxima get narrower. For I found on page 366 this nice little thing. We were talking about this earlier with the lab that we've done and whatnot. And so here we have the separation of the central maximums, or the minimum. We can talk about maxima here. And here is the distance that is separating the slits. And so we can say that these are proportional to each other. And so now the number of slits stays the same, but their separation decreases. So if the separation decreases, then it increases. So we can say the separation between the primary maxima increases. There we go. All right, let's tackle this last one. I directed you to page 379, but help can also be found in the data packet. We've got a resolving power written down from the data packet, so that's what the R means. So it is the average wavelength divided by the difference in the wavelength. And here we have, this is a number. M is a number, haven't you heard? No, not that number. It's the number of central magnitude at that angle that we're looking for. And this is the number of slits that we need. So slits, I'll just go there. So that's what we're looking for, okay? And I've done a little ahead of time here. So the average number, the average wavelength is 656.36 nanometers. And I'm just going to plug that in. Okay, so here we go. So I'm going to move this up. Sorry, you can't see that anymore. But, all right. So we've got 36 over our change. And our change in the two, the difference is just 0.18. Okay, and that equals 2 because 15 degrees is at the second primary maximum, and n, which is the number that we're looking for. All right, and if we do a bunch of math, it comes out to 1,823 slits per millimeter.